one, and it's reviewing some also basic arithmetic that you know, and one of those is the definition of prime number. A prime number is a number whose only factors are 1 and itself. For example, primes would be 1, 2, 3, 5, and 7, and so forth, because 1 times 1 is 1, 1 times 2 is 2, 3 times 1 is 3, 5 times 1. There are no other factors except for 1 and itself. So these are all prime numbers. And then they give you another definition. They say if a number has other factors than itself and 1, I should say and 1, right? If they have other factors, then it is a composite number. Sorry, I can't talk this morning. Composite number. So composite numbers would be numbers like 4, 6, 8, and 9. 4 because you have 1 times 4, but you also have 2 times 2. Or here you have 2 times 3. So they have other factors, then they're called a composite number. And what you need to realize, though, that is every composite number can be written as a product of primes. Product, remember, is the answer to a multiplication problem. All right, so to find these prime factorizations, you can use the factor tree or what we call the division of primes. And so you've all, like I said, done this before, but we just want to recall. So, for example, here is 12. 12 is a composite number. You can use the factor tree by starting off with the lowest prime number that you know of besides 1, which is 2. All right? So we're going to ask ourselves, 2 times what gives me 12? 6. And then do another tree and see if 2 will go into 6. 2 times 3 is 6. You know you can stop when you end up with primes and there's no more composite. There are no more prime factors because this is a prime number. So the prime factors, 2 times 3, taking each one of these, is that product, all right? That's 12 written as a product of prime numbers. You can also use the division tree, and I prefer the division tree because it's more obvious when you stop. Again, you say 2 goes into 12 6 times, 2 goes into 6 3 times, and we know we can stop here because it's prime. Again, you get 2 times 3. So here's the product of prime numbers that equal 12, that composite number. The book gives you a couple of extra things or notes. They said, remember that all even numbers are divisible by 2. Well, 12 was even, right? So it's divisible by 2. They also tell you to remember that all numbers that end in 0 or 5 are divisible by 5. Okay? All numbers that end in 0 or 5 are divisible by 5. I want to move that just over just a little bit. And the other thing, they tell you that if you know that the sum of the digits, if the sum of the digits is a multiple of 3, then it's divisible by 3. Well, let's look at it. The sum of 12, we have 12, so 1 plus 2 is 3 because the digits are 1 and 2. 3 is a multiple of 3, so that should tell you that this also is divisible by 3, which we do. We have a factor of 3. Here would be another example. 45. Well, if we add 4 plus 5, we get 9. 9 is a multiple of 3. So what that tells me is that 45 is divisible by 3. And I can test that. 3 goes into 4 1 times. We get 15. So 3 times 15. Notice if we add the 1 and the 5, we get 6. 6 is a multiple of 3, so I know I can take 3 into that again. And I get 5. So the prime factorization of 45 is 3 times 3 times 5. We also know that 45 is divisible by 5, right? Because we said anything ending in 0 or 5 is divisible by 5. So these are just some helpful hints in helping you figure out maybe where to begin. whether you're going to start beginning with 2 to divide it by, or 3, or 5. Now, the reason why we reviewed all that is because we're going to start finding the greatest common factor, GCFs. I'll refer to it as the GCF, but that stands for greatest common factor. The greatest common factor is the product of all the common prime factors. So an example of that would be if I asked you to find the greatest common factor of 40 and 50, you would do the factorization tree or the division tree and find out the prime factors. So I'm going to do this, and notice that it ends in 0. So I know that 5 will go into it. 5 goes into this 8 times, and 8 is even, so I know 2 will go into that. 4 is even, so I know 2 will go into that. And so when I get done, I ended up with a prime. We're going to do the same thing here, and 5 goes into that 10 times. 5 goes into that again because it ends in 0, and so we end up with a prime number. So the GCF, so here's the prime factorization of 40. 5 times 2 times 2 times 2, and this one is 5 times 5 times 2. Excuse me. The GCF will be basically all the common factors that they have in common. Well, here they have 1, 5, right? So we can write 5 in each. Here they have a 2. Well, they've got a 2 here, so we can write that. And there is no more common 2s or common 5s. So the GCF of 40 and 50 would be 10. The GCF of 40 and 50 would be 10. And that's how you find the greatest common factor of 40 and 50, because 10 goes into both of them. Let's look at another example. Here we have, what is the GCF of 16 and 24? So you're going to do your prime factorization tree. I'm going to say 2 goes into that 8 times, 2 goes into 8 4 times, and 2 goes into 4 2 times. I can stop at the prime factorization. Here we got 24, 2 goes into 24 12 times, 2 goes into 12 6 times, 2 goes into 6 3 times. And so the GCF then, or the greatest common factor of 16 and 24, would be, well, we have 1 2 that's in common. We have another 2 that's in common. We have another 2 that's in common. And then we have a 2 and a 3. So this GCF is 2 times 2 times 2. Well, 2 times 2 is 4. 4 times 2 is 8. So our GCF is 8. So 16, 8 goes into 16, and 8 goes into 24. That's the greatest common factor. Now, some of you don't have to do this prime factorization tree when we're dealing with smaller numbers. Most of you might have been able to realize, well, they both have a common factor of 8. 8 is the highest common factor that they have, and you might have been able to come up with that in your head. If not, you can always go down to the factorization tree. Now, but what if I asked you to find the greatest common factor of 50x cubed and 20xy? Well, here you're still going to find the common factor of 50 and 20. For the exponents, you're going to use the lowest exponent of the variables. Well, that makes sense. Okay, notice that there's no y. There's a y here, but there's no y here, so that's y's aren't in common. They both have x. This one has 3 x's, and this has 1 x. So what they have in common is 1x. So you know the GCF, right, is going to be 1. It's going to have an x in it. And now you got to look at your numbers here and see what is the greatest common factor. Well, they're both divisible by 5, right? And we can just go ahead and work this out. What do we notice? They both have a 5 in common, right? And they have a 2 in common. So 5 times 2 is 10. So the GCF is 10x. Now, I can check that, right? Think about this here. Will 10x go into 50x? Yes, it will divide out evenly. And will 10 go into 20? Yes. So this is your GCF. Here's another one. So 12 and 15, we want to know what is the GCF of them. Well, 12 and 15, we know they're both divisible by 3. Okay, are they both divisible by 5 or 6? So you're looking at the factors. What do they have in common? And so in this case, they're both divisible by 3. And then they both have x's. This one has 7 and this one has 4. So they have 4 in common. They both have y's. This one has 3 y's. This one has 13. So we're going to go with y cubed. And so this would be the GCF of these two right here. Now again, if you didn't know it was 3, you would just take that 12 and 15, do your factorization tree, right? Oops. Right, they had a 3 in common. That's all they had in common. That's how we got that GCF of 3. So that's just your review there of 7.1 is finding the greatest common factors.